A transformer is an electromagnetic device, meaning it uses both electricity and magnetism. Its primary function is to change one voltage into another while electronically isolating the two halves. So you end up with two different circuits that are completely separate in every single important way, unless you connect them again after, which sometimes you will. We'll get into that later. A transformer can increase, decrease, or keep the same the voltage. So it can step up, step down, or just isolate without doing either one. The most common type of transformer you'll find will be in little wall warts, for like wall chargers for your phone. These will step down your mains voltage, 120, 220, or whatever volts, to the 12, 9, 6, 5 volts that your thing needs. You'll also see step up and step down transformers for the mains on the power lines. They step up the voltage to transfer them over long distances and step down the voltage to come into your house. An isolation transformer that does not change the voltage. This is primarily used for when you do need an isolation circuit for safety reasons or signal stability reasons to reduce noise or whatever. And you can also do something called impedance matching for audio or other analog signal processing, another thing we'll get into in the future. Conceptually, a transformer is just two inductors stapled together. Obviously, this ignores a whole bunch of physical details of how transformers actually work as devices. But conceptually, it's a really good analogy. It makes them much easier to understand and use if you just think of them as paired inductors. There are a ton of different ways to make transformers that each have their strengths and weaknesses for different applications. As is the theme on this channel, I'm going to stick with the simplest and easiest one that not only is simple and easy to use, but simple and easy to make yourself. This is an inductor. The metal is a magnetic material, not a magnet, but a magnetic material. All I did was I took my wire, the magnet wire that has the lacquer on it, instead of regular insulation, and I just coiled it around this core. Then I put some electrical tape on. That's not necessary, it's optional. It's just to hold it down nice and neat. I'm going to be demonstrating with my inductor rather than my actual homemade transformer because I've already managed one time to drop the transformer off the side of the table with all the wires still attached. So if you don't mind, I'm going to leave it right where it is. Now this inductor, this part here, the C shape, the part sticking out here, that's not doing anything, so just ignore it. So just pretend it's like that. The reason is I got two halves of this, which is intended to make a particular type of transformer that has coils on one side and the other. But I ended up not using it that way, so this is fine. It's just this part sticking out doesn't do anything. So a simple inductor. So this is half of a transformer. I have the magnetic material in the core. Around that magnetic material is a coil of wire. This is a cross-sectional view, so we're looking at it down the end if we sliced it in half. So it's got the coil around it, and then just some electrical tape, right like so, which again is optional. It's just to keep it neat and tidy. So this is an inductor. We've gone over inductors. Use it as an inductor. It'll work fine. I mean, it's not a good quality inductor. It is homemade, but it is perfectly functional. So what would happen if I just put another coil of wire around this? Just coiled the wire over the electrical tape and then put more tape down. And what if I even did it twice? Another coil of wire, another layer of tape, another coil of wire, and a final layer of tape, just so it all doesn't fall apart. So you'll just have the wires coming out, so you'll have 3 wires on one side and 3 on the other, 2 wires per coil. Now that's a transformer. This is why I say it's the easiest kind, because you only need one thing. You can do it on a nail if you want, just make sure it's an iron or steel nail. So what happens is you take only one of these. Let's say this one. Let's say that this inner coil has electricity across it. That coil, I put an AC signal across it, just like it's an inductor. I want to create a changing magnetic field. That magnetic field is going to extend outward through the other 2 coils. Let's say I don't attach a voltage to those. Let's say I attach a load to those. Remember how you can move a magnet near an unpowered coil and it will create electricity in the coil. And you can put electricity through a coil next to a magnet and it will attract the magnet and thus move the magnet. So this is how we translate between. So you've got both of those put together. A changing magnetic field is being created by electricity next to a coil, so we're just skipping the permanent magnet. So the idea is just that the field encompasses the whole thing, and then the other 2 coils are in there and get affected by the field. Now, electrical tape is actually a terrible choice for this because it's thick. You don't think it's thick, it's just tape, but in the electronic world, electrical tape is really thick. There is a special kind of tape you can get that is excruciatingly thin. It's like hair thin or even less. That's the kind of tape you should actually use for this, but this is good enough. I'm just demonstrating. But having the electrical tape just makes this less efficient because everything's further away. So you might be asking, how do we have the magnetic field from the changing current inducting into the other two? It's not moving. All the demonstrations I've done, you have a physical magnet moving. That's how your water wheel creates electricity. That's how your motor receives electricity in the form of magnetism to turn it. Well, think about how a magnetic field works, and think about frames of reference. Let's say we have a magnet, and this magnet has lines of force. This is just how we draw it. Obviously, the force is not really lines. You know what I mean. Let's draw a few more. So this is a magnetic field, and this right here is a spot. X marks the spot. At that spot, there is a particular magnetic strength. Let's say it's 3. It doesn't matter 3 what, it's just 3. Well, that doesn't do anything. We know that we need a moving magnetic field to cause electricity at that spot. So we move the magnet. Let's say this spot here is 4. So that's magnetic strength 4 because it's closer. If I take this magnet, I don't move the spot, I move the magnet. So I move the magnet closer. The magnetic strength increases from 3 to 4. So there is induction. Electricity is generated in that spot. But let's say we can't move the magnet. Let's say we move the spot instead. So the magnet stays where it is. And I take this spot and move it into the stronger part of the magnetic field. So once again, the spot goes from 3 to 4, and there's motion. And if you're familiar with physics and the concept of reference frames, you're right at home with this. It doesn't matter to the spot whether the magnet moved closer to the spot or the spot moved closer to the magnet. There was still motion where the magnetic strength increased from 3 to 4, and thus current was inducted or induced or whatever it is. So that's fine and dandy, but what if we can't move either one? What if this is an inductor rather than a permanent magnet? What if it's an inductor? We're putting a particular current through it right now, and that's creating this same strength magnetic field. So it's a coil, so we got a coil that's creating a permanent magnet, and this is the lines of force. So we don't move the coil, we don't move the spot. What if we just turn up the current? We turn up the current to whatever point required to make this spot 4 instead of 3 strength. The field did not move. The coil did not move, the spot did not move, but the strength still increased from 3 to 4. Well, how does the spot know that? How does the spot differentiate between motion or just the field got stronger? It doesn't. It can't. It doesn't matter. That's how a transformer works. Your magnetic field gets stronger and weaker and goes the other way and comes back this way and goes the other way. You know, any varying signal. And it inducts because it's the same as if there was a moving magnet. A changing magnetic field, a moving magnetic field, both do the same thing to a spot or to another coil in that field. That's how it works. So that's how it can induct, but how can it control the voltage? Well, let's say you have a varying signal. Let's assume it has all the power it needs. Don't worry about power. Just figure this has unlimited power. So we take this signal, we come around here, and we have a coil. This is an inductor. You'll notice there's no resistor. There are times you'll put a resistor. There are situations where you want a resistor, but fundamentally you don't need one. Signal and inductor, and that's it. Of course, not actually an inductor. It's half of the transformer, but conceptually we're going to say it's an inductor. And then let's just do this to make it look nice. And then we have a load. Here's a load. A load is a resistance, impedance, reactance, or whatever. Doesn't matter how that comes to be. There's just, in some way, there is resistance to the flow of electricity. There is work being done, even if it's just heat dissipation. There is some resistance to the flow, and it's connected over here to the other conceptual inductor, the other half of the transformer. This is the simplest setup for a transformer. So pretend there's no load for a second. Just worry about this half. You have a signal and an inductor. So the two parts to an inductor, the first is the changing magnetic field. Current goes up, current goes down, magnetic field goes back and forth. We've already been over that. So that's happening there just fine. There's a reactance in this inductor. Based on the frequency of the signal, higher frequency, more reactance, which means more effective resistance. So if you have a very high frequency signal, then the inductor on this side itself is going to resist a bunch of the flow, and it's going to control your power usage. So in that case, you don't need a resistor in here. If you have an incredibly low frequency signal, you may need a resistor, or you just need parts that can handle more power. Either one. But the only reason you'd ever put a resistor here is to limit the possible current through the inductor because the frequency is too low and it's basically a short circuit at that point. Of course, if you have a resistor, it's cutting your maximum voltage, so that's not good. But as long as you turn up the frequency, you're fine. The other thing thing you need, though, is a load. If you don't have a load, then this is just an inductor. By adding a load, it becomes a transformer. If this is literally unplugged, the other coil doesn't do anything. It's an open circuit. It doesn't get inducted into. I mean, a teeny tiny bit, but negligible. This acts as if it's just an inductor, and it's just going to waste your power, possibly overload. But if you put a load there, what happens is this creates a magnetic field. The left inductor is creating a changing magnetic field, which is inducting into this inductor. The magnetic field is the same. It's intersecting both. And the changing magnetic field, we've established, creates electricity, which goes through the load. The load resists the flow, which means the load is resisting the induction happening in here. It's hard to intuit that, I suppose, but just trust me, because I'm trusting the very smart people, and obviously it works. Your resistance here, this load, resists the current going through here because it's being created over here, but it's not letting this side create as much current as it wants. It's providing enough resistance that the magnetic fields are linked, and so this one is kept under control, and this one is kept under control, and so the whole thing here is kept under control and doesn't become a short circuit. So you might think, oh, what happens if the load is unplugged? What happens if you plug in your wall charger but you don't plug your phone into your wall charger? Well, there's all kinds of advanced ways to do it, but the simplest way, that's wasteful of power, but works perfectly well, is you just have a high value resistor here. Make it 10 mega ohms, it doesn't matter. Make it a gigantic resistor in parallel with the load. So when there's no load, you have a gigantic resistor, which acts as a load, which keeps this under control, so this is spending power to keep the voltage on, but it's not shorting, because it has something to work against. This load is keeping the magnetic field in check. And when there is a load, you've got your parallel resistance, so if this is 10 mega ohms and this is 10 ohms, then the parallel resistance just goes away. I mean, there will still be power going through there, but it doesn't matter. So you can do that. But that's just a safety measure. We'll not worry about that anymore. So once again, I've explained how voltage gets from one side to another. Sort of. I know this is taking a minute, but remember, simple is not quick. You might think the more the load here, the less current goes through here, but that's not true. The more the load here, just by Ohm's law or whatever, the less current goes through here. So what happens is you have a peak-to-peak voltage, because it's a changing signal, right? It's not a DC signal. This inducts a peak-to-peak voltage on this side, and then you get a peak-to-peak voltage here, which is electrically isolated unless you put a wire. So the load, think of this as a battery. Think of this as another battery. This is an EMF, an electromotive force, and so is this. They're connected by the magnetism, but the standard electricity, electron flow, whatever you want, is not connected if there's no wires. There's no connection here. So they are completely separate EMFs. So all you have to do is think about, this is a battery, this is a signal, right? This here is just a signal, right? So you've got voltage, you've got resistance, you can determine current. Higher resistance, less current. Lower resistance, more current. Voltage stays the same. And you're thinking, what about the conservation of power? The conservation of energy? If this is consuming more power, surely this has to go up too. Some of you are shaking your head like, what are you talking about? Of course not. Listen, this is not intuitive for me. I'm explaining for people like me. If you already get it, smart. Yay, good for you. The thing that took me a little bit to grasp is that this is creating a separate EMF completely regardless of the load. But you just said you need a load. Yes, you do. You need a minimum load. And I'm sure there's some physics formula out there that tells you what it is. There is a threshold, and this is what confused me on my oscilloscope. If you turn the load down far enough, this goes crazy, my power supply maxes out, and the circuit just stops working. But all you have to do is turn the load up a little bit, just barely over a k ohm for my particular setup. And the second I did, the second it reached that one critical level, bam, it was happy. And then I turned it all the way up to 2 mega ohms. I was wiggling that thing, I'll show you. Wiggle that thing all you want. Between 1 mega ohm, 2 mega ohm, 10 k ohms, it does not affect the power draw. But if you turn the load down all the way, this goes crazy. So all you need is a threshold. All you need is just enough of a load that it is affecting this enough, this right side inductor enough, to affect the magnetic field enough to create just enough drag that it becomes a transformer. Basically, if your load is low, this is a inductor. This is an inductor. And if you turn the load up just enough, it links them, it becomes a transformer, and then it doesn't care about the load anymore. So that's something fundamental to realize. Turning the load up and down changes the current through here because of Ohm's law, because of this being a separate EMF, like a battery. The power consumption through here, if there's a minimum load, is steady. It does not change. It's just creating, let's say, a 4-volt peak-to-peak signal. It's going to spend, based on the frequency, the inductance, blah, 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 it's going to consume a certain amount of power to create a 4-volt peak-to-peak signal across here. And then from there, it's just going to stay steady. It doesn't matter how much load there is. It's going to stay steady. And then the load just controls how much current goes through here. Because current equals voltage divided by resistance, and power equals voltage times current. And that is always going to stay the same. The amount of power available in here is constant based on the voltage. Please tell me if that part still confuses you. I can always do a follow-up video. Like I said, it confused me. But that's pretty much the most thorough explanation I can make. So what determines the voltage? Step up, step down, or isolation? It's the number of turns. If you take the wire and you go around one time, that's one turn. 2, 3, 4, 5, 6. Number of turns is just number of times the wire has gone around. And because these, on my transformer, there's only one here, but on my transformer there's 3 coils, they're all electrically isolated. Because they got electrical tape, they got the lacquer insulation, so they can each have a different number of turns if I want. But for me, they all have approximately the same because I just did it along the length. But let's say we have 3 turns here and 1 turn here. So let's just say that this is a 3-strong field. Whatever that means. There's 3 coils, which means, well, there's 3 turns in the coil, which means the 3 are interacting and creating a 3-strong field. But there's only 1 coil for it to interact with, 1 loop, 1 turn on the other side. If I put 2, it can interact with both at the same time, and it can induce current in both at the same time, but there's only 1. So however strong this is, and you could make it 4, 5, 6, however strong you want to make it, but however strong it is, it still only has 3 turns to interact with 1 turn. So if you add a turn over here, it's going to double what this is receiving. It's going to get another dose and another dose of 3-turn strength. So let's say we have 3. 3 turns over here and 3 turns over here. Intuitively, it is 3 creating it and 3 receiving it. This is an isolation transformer. The voltage does not change because 3 of them are combining their forces to create a 3-strong field, but each turn is only receiving 1 slice of that, but there's 3 turns, so it's receiving 3 slices, so it gets all 3. But if there's only 1, then it's getting only a third of that. Because it's 3 strong, but it's only interacting with 1 coil. Let's say I had 6 coils. So you've got 3 strong, but it's interacting with 6 coils. 6 loops. I keep changing the word. If 3 is the same voltage and another 3 is the same voltage, it's interacting with 2 sets of 3. See, that's more. So you get a turn ratio. If you have 3 over here and 1 over here, that's a ratio of 3 to 1. A 3-volt peak-to-peak, not RMS, but peak-to-peak. A 3-volt peak-to-peak signal on this side will create a 1-volt peak-to-peak signal on this side. If you add 2 more turns, you get 3 to 3 ratio. 3-volt peak-to-peak will create a 3-volt peak-to-peak here. Add another 3, and you get 3 to 6, which is also 1 to 2. So a 3-volt signal here becomes a 6-volt signal here, peak to peak. And it doesn't matter if it's 3 turns and 6 turns, or 3,000 and 6,000, or 1,500 and 3,000. It doesn't matter how many. It's only the ratio. That's the only way I can think to intuit this. You know, you can take a physics class and you'll get all the fancy flux integrals, but to just think about how it works, this determines how strong the field is, how many turns is, how many strongnesses it is. That's the word for the day. And then you're trying to transmit that strength, and you have so many turns to interact with at the same time to do so. So very simply, that is how you determine the resultant voltage. It's the turn ratio. So what happens if you do put a wire here? The same as it happens if you connect any power supply. Both of these rails, both of these lines, these points, become the same voltage conceptually, because it's all about the relative voltage. What does 0 volts mean? What does 3 volts mean? What does minus 2 volts mean? routine. We pick a voltage on one of the power supplies. We say, okay, this is our main power supply. And this spot, which can be the negative terminal of the power supply or battery, we say that spot is 0. And then everything else, positive or negative, is relative to that. So you can do the same thing here with no wire. And you could say over here, my second power supply, this end is 0. And so positive and negative measured relative to that. But if you don't connect them, then between each other it means nothing because it goes down to charges at that point. But if you connect them, and I've gone over this in whatever video, I don't even remember, but this is just how you make a dual power supply anyway. I connect my 2 power supplies and join them. Now, what happens is we say this voltage is 0, and this voltage is 0. So whatever voltage is here and whatever voltage is here, they're both 0. So any voltage relative to that, it doesn't do anything electrically. It doesn't force the charges to change. It just connects them so that when we measure either point, or a point in either circuit, it's relative to this shared potential. That's all it is. So you can do that with a transformer, and you may want to, or you may not. So I'm not really sure what else to say, so I'm just going to say, tell me in the comments, and I'll follow up. Right now, I'm just going to show you in my breadboard. So here is my homemade transformer, which I am being very careful to not drop off the table. I have the 6 wires sticking out that are just connected by alligator clips into my breadboard. My oscilloscope is going to create a sine wave, and I'm going to start at 8 volts peak to peak. My power supply, I'm going to do 100 milliamps limit on both and 7 volts on both. So plus or minus 7 volts is 14 volts peak to peak power supply. The signal is going into a simple power amplifier. It's an op-amp with a push-pull. It's the only power amplifier I've gotten to work with an inductor. I'm going to have to do more research. I've tried Darlington, emitter follower, and other things, and they all just goof up the signal. But the unity gain with push-pull seems to do okay. So anyway, it's just power amplified and isolated, that's all it is. And then I've got my 2 mega ohm potentiometer as my load. Now there's one other thing. Remember I said I have 3 coils in here? 2 of the coils are connected. 1 coil is powered, the other 2 coils are in series. So effectively, they're double the turns. So if you have 3 coils that all have the same number of turns, and you take 2 of the coils and put them in series, effectively that just has double the coils. It doesn't matter that they're on top of each other. All that matters is effectively you coiled it around once, and then you coiled it around again. So it's 1:2 ratio, so I should be doubling my peak-to-peak voltage just by connecting 2 of the coils in series. So this allows me flexibility. By having these 3 coils that I can connect in series or not, I can have a set of 2 1-to-1 transformers, or I can have a 1-to-2 transformer, or a 2-to-1 transformer, however I hook it up. But in any case, here's the signal. So right now, the input signal is 8 volts peak-to-peak, but these divisions are 4 volts each. So 4, 8, 4, 8, that is 16 volts peak to peak. And I can move my, where's my oscilloscope probe? Here it is. If instead of measuring that, I measure the input signal over here, you can see it's half the height and much cleaner. So 4 to 4 is plus or minus 4 or 8 volts peak to peak. And when I measure the 2 coils in series instead, I haven't figured out why it's doing that. It's probably just my cheap Chinese power supplies or the way I've got power amplification. But in any case, it's a nice sine wave, double the voltage. And it's more voltage than my power supply has. My power supplies are only providing 14 volts peak to peak. This signal is 16 volts peak to peak. So I'm using power to increase the voltage, 1:2. But in any case, it's using about 82 milliamps at 7 volts, because it's not, if you're calculating power, it's milliamps times 7 volts, because each power supply is separate. They're just joining their forces. So 7 volts times 82 milliamps would tell you how much power I'm using for this whole circuit. But first, I'm going to change the load. This is a 2 mega ohm potentiometer, I will remind you. 2 mega ohms. And it's measuring, this is the signal the load is connected to. And I will now turn it up and down. So right now it's at 2 mega ohms. So I'm turning it up and down and up and down and up and down. It's varying by over a mega ohm right now. And you'll notice my power supply is not wiggling. The signal on the oscilloscope is not wiggling unless I turn it down too far. But if I wiggle it just 1 mega ohm, it's fine. If I turn the load all the way down, then my power supplies go into current limit mode, which is why the signal looks goofy, because it's not got enough power. But it basically shorts out the inductor, because it doesn't have enough reactance to limit it to 200 milliamps. But if I turn the load up just the teeniest, tiniest bit. I am breathing on this right now, and you can see that voltage go up and up. So turn it up, and boom. I turn that trim pot basically 1 degree of its rotation, and it's fine. And then I just reach in and turn it all the way up to 2 megaohms, bam, and it doesn't matter. So that's the illustration that the load only has to be a minimum amount. The other thing is the frequency. So let me go in here and adjust the frequency of the wave. And it looks fine. It looks fine. I'm just adjusting the wave. If I do it carefully, I said, the faster you turn the knob, the faster it changes. So like in this range, carefully in this range. I do not like that. The faster you turn the knob, the faster it goes. But you can see right now the signal's fine. Now observe the power supply. As I turn the frequency up, the power consumption is going to go down and down and down and down and down. See? And then I turn the frequency down, the power consumption goes up. This is because I do not have a resistor in the circuit, in the primary side. I guess I forgot to mention that the electrically connected side is the primary and the side with the load is the secondary. So the signal's on the primary, the load's on the secondary. Yeah, anyway, that's it. So the primary side has no resistor, so this is purely the reactance of the inductor. So I can turn the frequency down and down and down, and it doesn't care until 100 milliamps limit. If I turn it down more, now my signal goofs up because these are limited. And it's fun, if I show you, it's kind of fun to look at it, how it goofs up. It kind of splits at these points. I just think that's cool looking. But anyway, so this is not a malfunction. This is not enough power. If I turn the power limit up, the signal would go back to being perfectly fine. So it's just the way I have it set up is it's trying to take too much power, but it would work with more power. On the other hand, though, if I turn it up and up and up, at a certain point, it's going to start goofing up, and there it is. See, now look how fast it's changing? And the voltage goes down, and the voltage goes down, and it turns into, it's a little hard to see, but it turns into a triangle wave. Mostly a sort of triangle wave. It's being filtered by the impedance, the reactance rather. At this point, the reactance of the conceptual inductor, the first half of the transformer, is so high because I've turned the frequency up so high, it's right now at 26 kilohertz, that it just starts eating the voltage. So the signal just goes away because it's consuming way too much current, or not consuming, you know what I mean. It's conceptually consuming it so that it's not passing it through to the signal, and the signal just goes away the higher the frequency goes, and then you can just bring the signal back and it's fine. And you can measure the range. In my current setup, it has enough power to go down to about 3 kilohertz, and then the signal starts goofing up about there. So let's call it 9.5 kilohertz. So this is the operating range of this homemade transformer with no primary resistor, with this power setup, with this power limit, this particular setup, blah. And then finally, I just change the amplitude, and all that does is just change the amplitude of the signal. So if I put it down to 4 volts peak to peak, now the output is 8 volts peak to peak, because it's still 1 to 2, and of course we use less power because it's less amplitude. And we'll put it back on 8. So that is a transformer in action. So fundamentally, that's everything you need to know about a transformer. At this point, you could just read the spec sheets or sales documentation or whatever for your particular transformer, and it'll tell you how it behaves, but you understand the concept. So whether it's a single core, multi-tap, whatever, you'll know what that means. Or at least I hope you do. If you don't, let me know, and I'll fix that. So until next time, I'll be seeing you.